Yeah, I think the one is the cable extension is connected to this um, docking station. I will explain the online participant that we're gonna get started soon, but not exactly right now. So my performance continues to be equally poor that it was yesterday.
In the meantime, can you start the projector and everything? Because
Yeah. Okay, a little bit of mic check. Okay, a little bit of mic check. Okay, online participants, it is at 10:15, but we are still unable to get started as I forgot my camera to my office. So Mustafa is currently running to pick it up. So as soon as he's back, then we can get started. And another problem we have here is that, I don't know, still again, the protectors are not willing to cooperate. I don't understand why. It's every single Tuesday, the same problem over and over again. Is it the protectors are still nothing? Oh, okay. Now at least one problem is solved. The projectors are on. This television, you might want to flick that over to see that, because I don't want to see this. How is this one is empty? This one is empty. What about that one?
it's okay.
It's okay. 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 No. Again, so we have 25 online participants, but we are not able to get started right away because we're still missing the camera and the cable extension. And Mustafa is currently running to take it. I forgot them to my office, but Mustafa is trying to fix this. And as soon as he's back, then we're gonna get started. But we are. Okay, also not displaying so well. Very good. All other things said, except the camera is still not working because it's not here. But as soon as we going to get it here, then we're gonna go. So the camera, and then we're gonna go. Have you guys took these exams earlier? Because this is something that is a little bit new to me. So you are familiar with this concept of exam? You're not familiar with that? Okay, so, but you guys have a time slot reserved? So what you need to do is that you need to be there on timely manner. And then what next, you just get in. I think you need to have your ID with you. Key. Key. What's the key then?
The electronic key to open the door.
Oh, okay. So you need to have the key to open the door.
And you go in, and you already know which computer you are assigned. You go to the computer, log in, and when the time starts, you start at the time.
Okay, right. So, and then once you're done, then you're done.
Yeah.
Do you need to have your ID with you?
No, you don't.
Huh. Okay, but so first thing that is extremely important, you have to have a time slot reserved.
Yeah.
And you have that already.
Yeah.
Good. Okay, then you know where to be. You know the exam, where to physically to be. So there's certain places, one place only in this university, isn't it?
Yeah.
And then there's a dedicated computer for you, so you know the ID number of the computer. You get in, you start your exam, you go away. So it's not too complicated. Okay. All right. Sounds good. And then what you can do then? Yeah. Yes.
What kind of login do we need? The Modal login?
Right. First time that I experienced an exam like this. It used to be in a Modal, but of course Modal exam doesn't make much of a sense today because of ChatGPT and others. Right. So next week, no lectures. So entire week will be no lectures at all. It's only exams. So I think at the university will be very quiet next week. Not busy at all. Okay, so a few more minutes and then we're gonna go. So then we're gonna get this camera and then we're good to go. And like I say, we are not gonna practice this presentation, my ERC presentation today. Reason is this. I had an exercise yesterday and it was like simulating the entire panel discussion. And that was really awful. That was really, really awful experience in many different ways. You know, the presentation was a little bit chaotic that I made. It wasn't very good. It was a little too lengthy, not much too lengthy, but a little too lengthy. And then, you know, I got a lot of criticism from guys like Mustafa. He was like, okay, this was no good at all. So you need to go back to your home and rethink the whole story. And that's what I'm doing right now. I'm like just thinking like, what the heck to do? And I think of this whole business about, I need to take off this mic system and put it back. Okay, it's back. So I really need to think again to be clear how I'm gonna sell my story. After this thinking, I will get back to you. So next lecture will be 4th of March. And then I have my revised presentation for you ready, but not today. And I'm seriously thinking that I'm over speculating the whole business about the ERC. Too much thinking. I think that's the like real problem here. What do you think? What do you say? Okay, let me take this away. Check that we have the presentation. There's the camera. What's the name of the camera?
Dell.
Dell. Okay, so we're good. Very good. Okay, can you just check if it is correctly showing my face? So it's a little bit low. At least it looked at it's a little bit low. Yep. Sounds good. Yep. Sounds good.
And what about the adjustment mark? Left, right? Left?
Yeah, I think it is okay. Looks like it's okay. Okay, so we're gonna go now. Thanks, Mustafa. Are you gonna be here or you come back?
We have a meeting afterwards.
Yeah, but you don't need to be here if you don't want.
So, are you going to teach or just exam preparation?
It's going to be one single thing, 2 single things, and then we're going to do this exam preparation.
So
And
I
each of the
stay
questions
for
will be...
I skip the exam preparation. I stay for the teaching, but I skip
Okay,
the exam
all right.
preparation.
Okay, so hey, sorry guys that I'm late today. But now we're going to get started the last lecture prior to midterm exam. And today what will happen is that I'm going to close the story about the modal reduction techniques. There will be one remaining topic for next period, but that's not going to be too much relevant for us. We're going to look at these techniques, and we're going to look a little bit about the scaling, and we're going to discuss a little bit about reference condition. And that's it. Then we're going to close the case, and we're going to discuss how is that you can prepare yourself the midterm exam. All the questions will be given to you. And they're a little different that I provided to you earlier. Little different in a sense that I took many of the questions away because I feel that they are not necessarily relevant for us. So the only questions that are relevant for us will be shown. And there is not that many questions. I'm really hoping that this is going to make your life a bit more pleasant. And as promised, there's going to be voting action. Is there going to be a voting action?
Yeah, like as always.
Okay, there's going to be a voting that you can vote one question that will be in the exam, for sure, 100% certainty. And the one question that will not be there. And it's going to be based on whoever question will get the most of the votes. will be selected, and whatever get the vote, most of the votes not to be there will be taken away either. I mean, same way. So it's based on your voting. So please vote. The voting will be put it on today.
We can
Put it on today, and then that's it. You will be announced winners and losers, winner and a loser, later this week. How many questions we have? Is it 5 questions? 6 questions.
Yeah.
So is one of them is the one that you voted, and the others are something that it will be based on the lottery, isn't it?
Yes.
Okay, so now, if you go to exam, I mean that your fellow student goes to exam and send the WhatsApp to you right after that, hey, the questions are this. Don't believe that, because it's not necessarily your case. Because once you enter the exam, there is this lottery system that selects the questions to you. So the rest,
We want question the same, like the one that they picked.
the one will be same. The one will be same, but that you already know because it will be announced to you. So it's going to be not a secret. Okay, right. So what we discussed a week ago was this. You know, finite element model, as they typically appears, consist of very high number of degrees of freedom. And this is not going well with multi-body system dynamics, which comes with a very limited number of variables, very limited number of unknowns. Typically, reference condition, which describes this reference, translation, and rotation. You may call that as a rigid body translation and rotation, even though that is not necessarily the case. It consists of, in planar case, 3 coordinates, in spatial case 6 or max 7 coordinates. That versus the multi-body, that versus with the finite element equation of motion, which easily consists of hundreds of thousands of degrees of freedom. They don't get along well, number-wise, because the one number is low, another one number is way too large. So what needs to be done is that we need to reduce the one number, and we need to reduce the highest one, which is, of course, this one here. The finite element model needs to be reduced. The way we're going to make that to happen is that we're going to look what are the properties of the structure. And now, instead of looking the single elements or multiple elements, we're looking the entire structure. And we're looking the way the structure behaves. And based on this information, we can create something that are called modal, like modes of the deformation, possible deformation behavior of the structure. This typically comes from an eigenvalue analysis. An eigenvalue analysis is something that you can conduct by setting external applied forces, which is this one here, to be equal to 0. So it's nothing but combination of inertia and stiffness. So it's only the properties of the structure you want to study with. That's what it is. Now, with this trick that we are no longer looking the points, which are nodal coordinates, we're looking the entire behavior of the structure, we are able to reduce the number of unknowns. Okay, the way the structure can deform is set with this matrix here. Each of the columns of the matrix is defining the one way the structure can deform. How much this type of the deform contributes, the final configuration of the final response, that's unclear. That's something that is called as a modal coordinates. Combination of modal, these modes, and the modal coordinates tells you that how is actual like, real deformation of the structure. So this itself is nothing but the feature, but multiplying that with the P, that becomes to be actual deformation of your structure. All right, now, nodal coordinates and modal coordinates are related, and they are related because of these deformation modes. And now, because originally, this tells you the number of degrees of freedom in your system. Now, moving to modal coordinates, you can reduce the number of unknowns with a minor impact to your accuracy. Of course, this is a little bit of gambling. So if you do your selection of your modes incorrectly or improper way, your damage to accuracy could be significant. But the idea is that you know how to make this happen. When you know how to make it happen, your damage in terms of accuracy will be something that is easy to handle, is acceptable. All right, now with this trick, with this possible avenue which takes you from the nodal coordinates to modal coordinates, you can reduce your original finite element model or its size. Now when you do so, when you look at closely how is a new inertia properties related to this time to modal coordinates, not to nodal coordinates, this easily becomes to be a diagonal matrix. Because if your modes, your deformation modes, assume deformation modes come from the eigenvalue analysis, then each of these columns, which is representing the deformation modes, they're orthogonal, mathematically orthogonal. And when you make use of these properties, then your mass matrix becomes to be diagonal matrix. The same for a stiffness matrix, that too becomes to be diagonal matrix. That comes with a great benefit, because now you can solve any one of these modal coordinates knowing nothing about others, because they are not coupled, as is originally these nodal degrees of freedom. They are coupled. This stiffness matrix is typically diagonal in the structure. It means that you cannot just take an isolated degrees of freedom and solve that knowing nothing about others. You do need to know something about others, but once you have this modal reduction technique, here you go. You don't need to know anything about any other coordinates. And now this one here, what is made here, is that the forces that are first expressed in actual global coordinates, and then later with help of safe function matrix to nodal degrees of freedom will be now expressed in terms of modal degrees of freedom. So that's what is happening here in the right side of the equation. Okay. Now, when you nicely select your modes, you can have identity matrix as your mass matrix, and your stiffness matrix is something that the eigenvalues will appear to be in the diagonal components. Of diagonal components will be equal to 0. And this is how you conduct an eigenvalue, like mentioned earlier. You take the forces to be equal to 0, and that's why it's nothing but the properties. Never get confused about how is actual displacement, because it's nothing about the actual displacement. It's about the ways structure can deform. And you can get the natural frequency which comes from the eigenvalue, and then the eigenvector that tells the way we are after here. Okay. And eigenvalue, of course, that's the same than the natural frequency of the structure. And if you have a forces, typically, in the same frequency that the natural frequency of the structure, particularly if it is not in a location that is a node location, then you can get the response that is looking very, very bad. You get the resonance condition. Okay, we practice this. So let me just summarize this, because there's one more story related to this example we did a week ago. So we have this structure that consists of 1, 2, 3 elements. And we constructed the stiffness matrix and a mass matrix for this structure. Now look at this. This is a good example about block diagonal representation of stiffness. So it's not diagonal, but block diagonal. You cannot just take an isolated degrees of freedom like this one here and solve that by using nothing, knowing nothing about other degrees of freedom. That's not physically possible. Okay, anyways, in eigenvalue analysis, you have here stiffness and the mass, and you follow what was explained in the previous slide. You put here the lambda that in the previous slide was mentioned as a omega. Sorry about this confusing. Omega power 2. This, however, is what we're looking for. You solve the determinant of this equation here. You will get the polynomial of the fourth order. And the polynomial of the fourth order will have a fourth place that is crossing the 0. And these places are eigenvalues. These are the eigenvalues. The numbers are 0, 12, 60, and 120. Okay, 0 means that there is a rigid body motion. And there is a rigid body motion. Because, look at this. There is no boundary condition any kind in my finite element model. If there would be a finite boundary condition, it would be like, I'm going to attach this to ground. And when I do so, then the degrees of freedom associated to this node here will be booted to be 0. So meaning this column here, this row here will be altogether zeros. That's the way you can introduce the boundary condition in your finite element model. Okay, but no boundary condition. So no boundary condition, as we can take this reference motion into account by using this body reference coordinate system. All right, so we can get the eigenvalues by substituting the eigenvectors. We can get it by substituting the eigenvalues one at a time to this equation and solve this vector. Example here is an eigenvalue number 12. You submit this information to this equation. You're going to get 4 equations, 4 unknowns. So it's solvable. So you solve these 4 unknowns, and you're going to get eigenvector, which is the way the structure can form. Another eigenvector, so like this is the one that is related to number 120, is looking like this. So it's just the way the structure can form. If this would be multiplied by modal coordinates, then it becomes to be actual displacement. But before that, it's just a way. And this is a way. This tells you how much you're traveling in this direction. If you have a way, but not knowing how much you need to travel to this particular direction, this information is no good for you. You cannot get the actual physical displacement. Two things needed, the way and amount. This is amount, this is a way. All right, scaling. I mentioned briefly a week ago that the scaling is something that is often used, because what the computers really like is to have numbers that are as close to the number 1 as possible. And what they hate the big numbers. The numbers that are like, just to give you an example, if there's a 10 power to 10, this is what they hate big time, because it's a big number, hard to deal with. They also equally going to hate if it is going to be really small number, minus 10. They don't like that. And that's simply because the computer accuracy becomes to be a limit if you have very high or very small numbers. So to solve this problem, usually when you do the simulation, you want to make everything, all possible numbers to be as close as 1 as possible. That's the optimal point. Now, in that sense, because these deformations are just the way, and you can multiply this deformation by any number you want, because it's still a way, nothing but the way. When we multiplying these ways by a number is called scaling. And one of the most typically used scaling is to normalize eigenvalues with the mass matrix. This is called mass normalization. You can do the stiffness normalization, but it's not commonly used. It's just meaning that you're going to select the numbers in such the way that the mass matrix becomes to be identity matrix, as was shown. Where was it now? Not shown here. I think it was earlier here. Here. Look, it was saying that after the reduction, the mass matrix becomes to be identity matrix. It's not necessarily the case, but you can force these modes such the way that this is what comes out from this multiplication. How you do this forcing? The forcing goes such the way you take each of these deformation, which is modes, and you look at them one at a time, and you put them in equation like this. You have here the deformation mode that is then multiplied by number which you do not know what the number is. And then another one, this is the mass matrix, the full mass matrix of the system, deformation, and again the number which you don't know what it is. This equation must be equal to 0. Excuse me, 1. This needs to be equal to 1. And when you solve this equation, as you solve alpha from this equation, you can figure out the alpha needs to be square root 1 divided by 5. You do this kind of scaling, then your numbers becomes to be as optimal as possible for computer simulation. What about the others? So what if I want to use a second mode? Again, it's the same thing. Here's my deformation mode. Here's my full mass matrix deformation modes. This is unknown. This is unknown. And all that needs to be equal to 1. So once I solve it, this is going to be 1. Oh, this, by the way, is not the second mode, but this is the mode associated to number 120. So look what I do here. So there were a total of 4 modes. The one was associated to number 0. One was on number 12. Then was a 60 and 120. So I'm using this guy and this guy, but not using this one and not using this one. Why? Because I'm reducing the size of the problem. And assuming that deformation associated with this natural frequency is not what I'm interested in. This is an assumption. It may be something that eventually is a wrong goal, and I need to go back and revise my thinking. That's possible. Anyways, now with these 2 modes, these are the ways structure can deform, which are now scaled in a way that the mass will be identity matrix, and stiffness will be having the eigenvalues in the diagonal components. And when I do this final reduction, this is how they appears. Now the final equation of motion is going to be like this. This is my inertia associated to modal coordinates. This is my stiffness associated to modal coordinates. These are my forces that I express in terms of modal coordinates. And this is it. This is all that I need. Now I can take any one of these. Well, now there are 2 equations. I can take any one of them and solve it without knowing nothing about the others. So now this is a 1 degree of freedom by present problem. Becomes to be very pleasant to deal with. Fast to solve. Now what I'm going to do is that I'm going to get eventually, I'm going to get this P solved as a function of time. What I'm going to do with the P, I'm going to go all the way to displacement by using this information. And then if I want, I can get the strains and stresses if this is what I'm interested in. But this is something we're going to discuss a little later, not today. All right, this is how you can get finally back to the nodal displacement once you know your modal coordinates. Okay, this is it. One more story, and then we're done. Any comments so far? Yes, sir.
Why are we only using eigenvalue 2 and 4?
Yeah, that's a good question, because I'm making an assumption that those are the critical ones. But you can come and say, I don't know, Aki, I prefer like 3 and 4. Who is right? Depending on where you want to use it. And this is something that typically we're going to get back to this modal selection. How you can, if you have a lot of modes, which one of them are important? This is something that is quite obvious, but needs a little bit of thinking. We get back to this after exam week. Okay, I said that, this example, we introduce no boundary condition at all. If there's a good strategy or what, that really depends a little bit about things. But when you look at this, I have here an example about crankshaft system. And I want to model here this connection rod. Connection rod that is connected to piston and crankshaft. Both ends there is a revolute joint. And now, of course, if I wanted to model this, what would be the correct way to introduce the boundary condition, if boundary condition is needed anyways? Should I just, when I'm thinking about this connection rod here, should I just put that in a space, like here, like this, and just compute the eigenvalues without any boundary condition whatsoever? Or should I introduce these simply supported boundary condition, like shown here? Like this end is connected and this end is connected such a way that the motion in a y direction is constrained. Or should I even use a fixed boundary condition in one of the ends? Which is the correct way to go? How should I model this? Any ideas? Which is the correct way to go? So yeah, you're not allowed to answer, but you know, why don't we do the voting action? So who is voting for A? No boundary condition whatsoever, just a free boundary condition, meaning that is put it in a space, and then we conduct an eigenvalue analysis, and then you gotta bend it in a certain ways. That's it. Who's voting for that? No one. Okay, who's voting for simply supported beam condition? Okay, all of you, but not all of you. Who's voting for this one? No. 2 votes. 2 votes. Okay, let me ask this. How to set the boundary condition? What's the correct way? Oh, this is, by the way, not yet on. So, sorry about this. I was already in Socrates, but I need to put it on here. Launch. Okay, so it's on. I'm gonna wait a little while. You guys don't see this, but I'm gonna wait a little while to see how is an answer, how you guys are voting, and then we're gonna discuss a little more. And that's absolutely the last subject matter before the midterm exam. Which one is correct? Now this is easy. This is not so easy because all other in-class quizzes so far, there's like clear hints. Go this direction. Forget about rotation of particles. Forget about this and that. This time, not so clear. Okay, we got 0 answers so far. How come? It says LUT2, room is LUT2.
Yeah, 37 people.
But we got no answers. You guys did not vote it yet? You voted?
Maybe you need to refresh. Yeah, 9 people.
9 people. 9 answers only. Huh. 10 answers. 40 people in.
Like in modal reduction, when selecting the modes, is there any clear way to pick the modes?
To pick the modes.
Yeah.
There is a way. There is a way, but it's going to computationally, but you really want to play safe, there is a way to make it happen. And it's going to be based on how is each of the modes are contributing the strain energy. But the first thing that you need to know is what is going to be the total absolute strain energy of your system. And to compute that, you should actually use a full finite element model. And that's going to be hard. And now the question is, if you do so, if you're solving the full finite element model, why would you like to solve it again using reduced model? Because you already got an answer. So the better answer, or the better way to go, is that you have a limited set of modes. You use them all to compute the value, how much is the strain energy, and then you look how much each of the modes are contributing. But the problem is this, that if you want to change your work cycle or something in your model, you should redo that again. This is the only way.
By the way, can we ever use this mode participation factor in the modes?
Like, can we ever use what?
Mode participation factor, right? Something that ANSYS provides.
Mode participation.
In every deformation, like when you see the modes, like for example, in extraction.
Right. We could, but the problem is that they are changing as a function of time. So it could be a certain time that, like thinking that this classroom of students is a mode. It could be you that is contributing in the certain time, and then in certain other time it could be me, and then this other teams could be next. So it's not so easy to know. Okay, guys, I'm gonna take a look at this. So I'm gonna close the case. So we have 46 students, but only 26 answers. Let me see if it is this because of the refreshing. Oh yeah, we got more answers. Okay, here's the results. Which one is how much?
it's still increasing, so give them some time.
What? Okay, how is going to be the success rate here? How much? How much going to be the success rate? 100%. 100%. You guys all going to get it because it was so clear based on my explanation. Wasn't it? Okay. So the success rate is going to be 100. And here you go. 100 success rate because every single answer is correct. Everything is correct. What? Everything is correct. So this is very confusing. What is this? What is this? Like, how come they be all correct? This is because you know that you do know this based on your vibration classes from the pastoral level. You know that each of these boundary conditions are associated to different natural frequencies. So natural frequency is different based on the boundary condition. How come you have a same response or roughly same response regardless the way you're selecting your boundary condition? Of course, this is a special case, but it's a very informative for us because what we are interested in is that we're interested in a final destination. What is a final destination? It's a point, let's say somewhere in, let's say in the middle of the beam or any other location of the beam. That's what we're interested in. And when you have the reference coordinate system, which is a global coordinate system, what we really wanted to know, where is this point with respect to this coordinate system? Where you're going to travel there doesn't really matter. You can travel this location here and here. Or you can do the same here and here. Yes, it is, this distance is different than this distance, correct. But this distance, sum it up with this distance, ends up to be the same location. This distance with this distance, again, the same location. And what we are interested in, final destination, not the middle way. This is what is different because you know that when you have a vibration problem, you need to be very careful what is your reference coordinates. And the reference coordinate is going to be altogether different when you have a different boundary condition. We don't care that so much because we wanted to know where the particles within the body is located at with respect to global coordinate system. That's a different story. Okay, look at this. I'm going to write let me see if I have here a space enough. Okay, here's let's think of this as let's say cantilever beam. Let's make it like a structure like this. And then we're going to put the force here. How it's going to be. And we would like to know how is that deforming with respect to this coordinate system. Okay, the first case is this one here, where the reference coordinate system is not attached to the material point. So the deformation, when you take this one here, put it here, it's going to look like this. And the reference coordinate system is like here. Is that correct? Okay. Then you're traveling first here, and then you go middle of the beam. Okay? That's the first case. Second case is going to be like here, but the reference coordinate system is going to be rotated, but it attaches to this material point. Again, you're going to travel here and then here. So no difference in responses. And then the final one is going to be such that it's like here, or it's a big mess, like this. Same story again, one more time. This is very confusing. This took me a while to understand what is this thing. Because I know from the vibration classes that each one of them have a very different properties in terms of natural frequencies. But here, they are part of the nonlinear dynamics. Nonlinear dynamics consists of small linear pieces. It doesn't matter how you put these pieces together. Here comes the very last thing. This whole method where we're combining multi-body system dynamics and finite element models is called floating frame of reference formulation. That's what it's called. Where this name is coming from, the first word here is a floating frame. Floating frame. Okay, that refers to the fact that the frame that is where we're measuring the deformation is actually floating. And look at this case here. When you have no boundary condition, it is actually floating. It is traveling with the mode, but when there's a deformation, it is detached to material point. Here's an example. Look at this connection rod. If the connection rod is deforming like this, your reference coordinate system is going to be here. So it's not attached to any of the material point, but it's still not detached either. So it's like halfway, so it's half connected. So it's a fully connected when there is no deformation. And as soon as there's a deformation, it's be detached from a material point. And that's where the name floating frame of reference formulation is coming. Because obviously, frame here is floating. It is traveling and rotating, but not rigidly attached. It is traveling by floating technique. That's where the name is coming from. And this is something that I can ask from midterm exam, where the name floating frame reference formulation is coming from. I'm going to ask it for you. What the floating means in the floating frame reference formulation. It means that the formulation is still under development, so it's like floating until it's going to get its final form. It means that the body inertia can fluctuate. Inertia can fluctuate. All right? It means that the strain within the flexible body can be defined easily. It means that the body reference coordinate system can move from a material point of the body. So one only is correct. Oh, are you guys, sorry. So this is, Socrative is not yet on. So let me put it on here. So which one is correct? No, it's only one is, oh, you guys don't see it. Only one is correct this time. So it's a different story than any other cases. All right. Good thing. So my selling point is missing.
We can discuss it.
My selling point. So why this is important?
Because right now you're selling a solution for the problem that doesn't exist.
It does exist.
They don't know about it. You don't know.
Yeah. Okay, so less about me, more about why.
Yeah.
So it's not clear that you want to make the structures to be lightweight. They couldn't care. You know, what's the difference? So why don't we make it? Because heavy machinery states it's a heavy machinery. It's heavy.
Exactly. You know, as they say, if it works, why should we fix it?
Yeah. That is correct. That is correct. But look at the trends of many commercial products.
Even in the like for the cranes, like they have these problems at ports, like because the weight of the crane is limited. Like they can't have a heavy cranes in the ports.
Yeah.
In the ports, like they can't have a very heavy machinery.
Yeah.
So there are many ways to somehow sell your point, but you have to mention ways.
I guess. Good thing. Okay, so we got that for 38 answers already. Now this time, like I said, one answer only is correct. One only is correct. But which one is correct?
I think that you can show the result. It's 100%.
Honestly, how come this is possible?
Because it was way clear.
Way too clear.
Yeah.
But this requires that you listen to me.
Or
This is why I honestly, guys, this is why I love these lectures, because this is the only place in my life that somebody is listening to me. I go to my home and I go to the dinner table. I started to tell the stories, and they, oh, okay, oh, yeah, we don't care. So then here, you guys are listening to me. This makes me almost like emotional. Only place. I go and discuss with the Mustafa. Mustafa, yeah, I don't care. I don't care. Here you guys care. And I appreciate that. That's a great thing. That is a really nice thing. All right. Now, you want to have a short break? And then we're going to go this recap. How much you need? 5 minutes only. 5 minutes, and then we're going to do the recap. And again, like I promised. Or we can go directly if you want. This is up to you.
So how long does it take?
Not long, because we only have 21 slides. But many of the slides is only like this. Questions?
So if it doesn't take that much, I believe that they can go without the break. So this way you can finish it early.
Okay, so let's go without the break. Okay. Okay, again, here's the deal. So we are limited to these questions only. And these questions are less than what was offered during the course of these lectures. So less than that. So nothing outside of these questions can be asked. So I think that this is a good and safe deal for you. And this is forcing us to also to look at what is that we really wanted students to learn. And this is an amazing question because not long ago I do this like a mentoring for younger professors. And one of the younger professors, extremely talented professor, had a very extensive course about, one difficult subject matter in the mechanical engineering. And I asked, like, what is the one thing only you want your students to learn? And that's hard to ask. That's very hard to answer. Okay, the one thing, okay, I want them to know all these things, but one thing only. So that's why we kind of narrowing things down to make you guys focused, because focusing is important here. Okay, what kind of system can be analyzed using multi-body system dynamics? Of course, like the title implies, systems that are having multiple bodies that are connected together via joints. That's a definition of multi-body systems. We don't care about how big is a rotation. That is not an issue in a multi-body system dynamics. It can be small, it can be large. But the bodies need to be connected together via constraints. That's correct answer. Explain the concept of Euler angles. Euler angles is coming from 3 successive rotations. And you can select the rotations the way you want. That doesn't really make much of a difference. But typical way to select the rotation is a Z, X, Z. But the real key to understand the Euler angles is the successive rotations. That's what this is about. So try to memorize this. And again, when you write this, you don't need to explain it more than just what I explained to you. That will be the full points. Gimbal locking is an inability to differentiate what rotation is what. And this takes place when you have a 3 rotational parameters. So what can happen, like in the sequence that I just mentioned, Z, X, Z, that first and third are not necessarily something that you can differentiate what is what. And this is not the mechanical locking, but it's an inability to differentiate what rotation is what, because it can be 2 instead of 1. Rodriguez equation was based on this concept that you have a vector. You have the vector in arbitrary orientation in a space. You take an assisting vector, which is unit in length. You attach your assisting vector to origin of your original vector, and then you introduce in the amount of rotation that is theta. Now, this combination of this assisting vector and angle theta is a concept of Rodriguez equation. And this allows you to create 3 by 3 rotation matrix that consists of 4 parameters. These 4 parameters are this guy, vector v, component of vector v, and angle theta. This is your 4 parameters. Now, when you explain it, also mention that these 4 parameters cannot be selected freely, because assisting vector is unit in length. And because it's unit in length, you cannot select these numbers to be 1,000, 10,000, and 10. This is not possible because then the length will be other than 1. So that's your constraint. And that's why 4 parameters can describe 3 different rotations in space. Euler parameters was a name game. Was a name game that you're calling these angle theta and vector v parameters by names that are theta 0, theta 1, theta 2, theta 3. And with this name game, you can have another set of parameters. But it's still based on Rodriguez equation. So it's not that much anything else than Rodriguez equation with a different naming. That's what it is. Okay. moving forward. In three-dimensional case, body orientation can be defined using Euler angles and Euler parameters. Explain the concept of Euler angles and Euler parameters, which we already did. How these two methods are different. They are different because of the number of parameters are different. Usability is different because for humans, 4 parameters not easy to deal with. 3 parameters makes more sense because we used to deal with the 3 rotations. That's what we do in our daily life. So typically in commercial software, post-processing and pre-processing is carried out by using 3 parameters. And actual computing, then you got the 1 additional because the computers are better with the 4, humans are with 3. 4x4 matrix representation, how that can be used in robot kinematics, is a different kind of combination. Previously, we had this equation that we always deal with, R plus rotation matrix with the U bar. This is where the particle is located in a 3-dimensional space. Now, what we're going to do in a 4x4 representation is that we're going to express the rotation matrix and put it here in the upper left corner of a 4x4 matrix. This is where the translation will be. These are going to be zeros, and here's a diagonal component. That's what it is. Explain the method based on Denavit-Hartenberg representation. It is based on 4 parameters. This equation, as it is expressed here, this consists of 3 parameters, this consists of 3 parameters, which is typically not the case in robotics. Robotics, the bodies are connected in a few typical ways only. Translational joint, revolute joint, and those are the common ways of combining things. Now, this Denavit-Hartenberg makes use of these limited connection possibilities. And it allows you to create these 4x4 matrices for each of the robotic systems more or less automatically. How to relate angular velocity vector and the time derivatives of rotational parameters in a spatial case. This is this famous R matrix. Remember? In 3-dimensional space, this is a case. So where you can do this is this R matrix. You always need it. Always do. Because your kinematics, what comes first is angular velocity, but you don't like that. And why you don't like that? Because you would like to express everything by using generalized coordinates. And you can move from angular velocities to generalized coordinates with help of R. Makes it very, very handy, particularly when you're describing inertia properties of your body. Because otherwise you would need to express your inertia properties using 4 parameters. Big pain, very big pain. Okay, so these are the explanation. I did this explanation pretty much already. So this was kinematics. Euler angles was based on successive rotations. So successive is a word you need to remember. By the way, in this exam, is it so that you can only answer in English?
Yes.
Yes, that's the only option. It's English only. But the grammar mistakes or anything like that doesn't really make any difference.
Because if they answer in Finnish, you have to correct them. I can't give them more.
But in theory, isn't it? In theory, you can answer in Finnish and Swedish and English.
Even like, I don't know.
Swedish. There is no one except the Swedish teachers that can correct it. Okay, please use English. And my language knowledge is limited to Finnish and English. 2 languages only. My Swedish is already gone. That's never been there. But, it's a very sad story that my Swedish used to be stronger than my English. But it's gone. Because where the place we are located at, here, how much here in Swedish? Nothing. Now I've been watching this TV news every now and then in Swedish, and it's like, what is going on? I don't get it. Like, it's really hard for me to understand it now. Sad thing. Okay, here's a Rodriguez equation, the thing we just explained. These are the Euler parameters. This is the name game. You don't need to even memorize this much, but the concept is enough. And this is something is not even asked. Comparison. Singularity problem, always when you have the three parameters. Number of variables, 3 or 4. Usability, this is something we discussed. Robot kinematics, this is going like this. How is, by the way, in this exam room, are you able to, what if you want to,
people, they have registered
but what if you want to write this equation? Can you do that there?
You can add, for example, you can use different kind of files.
Ah, okay, so you can just, you can use a Word document.
For example, you have to use.
Okay, but again, still my advice is this. Don't put too much effort to memorize in any equations, but concepts. Concept what matters. Okay, like this one. If you're going to memorize this, it's going to be a big waste of your brain power. So don't do that, but memorize the concept. Even you don't need to memorize what exactly are these 4 parameters. That doesn't really matter so much. But again, the idea that the robot system can consist of few kinds of joints only. That's enough. That's enough for you. Okay, and this is it. So these are the different joints and the examples. And we discuss about this guy here. Ah, look at that. It's incorrectly written. Yeah, this is the correct way to read it. Okay. Then next set, how the linear strain displacement relation affects the deformation of the cantilever beam. Remember this, that if you have a force applying in a free end of the cantilever beam, when you have a linear strain displacement relationship, the beam cannot deform in this axial direction, because this is a second order nonlinear behavior if it deforms in this direction. This is okay if the deformation is like this much. But if the deformation becomes to be this much, this is you don't see this in reality. In reality, you see something like this. And this distance is something that you cannot capture if you're using linear strain displacement relationship. Except the concept of lamp mass approach. The concept is such that you have original typical beam-like body, and you break your beam-like body to rigid bodies. And between the rigid bodies, you're going to put the spring elements for all the 6 degrees of freedom, and that's going to be your lamp mass approach. Still using a wire ropes and certain applications, so it's still valid approach, still okay approach. Description of, this is a deformation, this is what I just explained. So no need to go further in this direction. Explain how polynomials can be used in the approximation of displacement in finite element method. Explain also how shape functions can be derived from the polynomial approximation. Okay, so everything started by you first defining what is a number of degrees of freedom. So if, for example, in a beam element, if you look at the transverse displacement, you have 4 degrees of freedom. So you need to approximate this displacement by using polynomial with 4 components. And these 4 components are constant component, this component that is like a linear component, and then I think the better way to write it like this, nonlinear, the power 2 component or power 3 component. These are the components. Pascal's triangle is very handy, particularly if you're using other than the line elements, solid elements, plates, and so on and so forth. It tells you how to select these polynomials. So they come from the Pascal's triangle. So the Pascal's triangle again is like this. So they're telling you how to select these polynomial, these guys, these ones. Now, originally, in polynomial expansion, these ones are unknowns. And when you replace these unknowns by nodal degrees of freedom, you get safe functions. Safe functions are orthogonal in mathematical properties, so they are not affecting each other. So they are only introducing the deformation to 1 degree in a nodal location. What the convergence rate means in finite-Selman method, it means that because the finite-Selman method is an approximate method, and it's getting better and better when you increase in the number of elements. And if you have here a graph, which is this is a number of elements, this is like the actual solution that you're aiming for, how fast you converge to this correct solution. It can be fast or not so fast, depending on the type of the element you're using, but you're always looking for a converged solution, the one that is already here, which is representing the reality. Okay, let me see. Physical interpretation of eigenvector. It is a way the structure can deform. And you can get it if you know 2 components, mass and stiffness. Is a way, but not absolute displacement. It's just the way that the structure can deform. Physical interpretation of eigenvalue is saying that the eigenvalue is that what is the natural frequency of the structure. So it's where is the resonance condition? What frequency of the resonance condition of your structure? You have many of them. So if you have a finite-Selman model with 100,000 degrees of freedom, you have 100,000 reference and resonance conditions in your model. So that's what it's referring to. How to conduct an eigenvalue analysis, I have the simple example about that. Mass normalization, this is this multiplying the eigenvalues with the numbers to make them to be close to 1. That's what this is about. Okay, so this was this polynomial selection. When you replace the polynomials by nodal degrees of freedom, you get the safe functions like this. Now they are more pleasant than polynomials because the physical interpretation is clear. So you know what they stand for. Whereas the polynomial, that's a little bit unclear. All right. This is a reduced problem. Let's look. We did not have any questions here. No questions here. Okay. In a finite-Selman method, the equation of motion can be expressed in terms of nodal degrees of freedom like this. The number of variables in the equation above can be reduced by using modal reduction approach. Explain the principle of the approach. Is this one. You're moving from nodal coordinates to modal coordinates. When you do that, you can reduce size of the problem and you eliminate the interaction between the different modal coordinates. That's what it is. What was this? Was the 7th wonder of the world.
Is it the 8th?
8th.
This one is the 8th.
This is 8th. So there are already 7 defined wonders.
75?
7 defined wonders. And this is number 8. This is 8th wonder of the world. Like, how come? You mentioned that, you're going to score well. All right, where the floating is coming from. It's coming from the fact that reference coordinate system is not necessarily attached to any of the material point, but is floating with the material point. And is detached as soon as the deformation takes place and comes back if the reference motion only takes place. Okay, this is what we discussed. This is questions from Adam. Which computational method can be used to study biomechanics? Give few examples and summarize the use cases that can be studied using selected methods. This came directly from Adam. And then if you study weightlifting effects on spine injury, how would you use flexible multibody dynamics for this purpose? Describe the assumptions of the model, which details are important, what would input parameters to be modeled, which quantities you would like to compute as indicators of the spinal loading. Okay, maybe this is the one that you want to vote it out. Okay, so the voting will be...
For sure it's going to take them at least half an hour to write that.
I think so too. Yeah. Okay, this is it. This is it. So we are not going to see you on Tuesday, next week, Tuesday, but week after that, and then I'm going to go back to my practices, and then it's going to be another week, and then it's going to be actual interview. And the results will be available in August, I think. I will let you know, guys. Okay. All right.
Yep.
Lunch will be next. Lunch break. Oh, yeah.
Are all the questions in the exam weighted the same?
Yeah.
Same points?
Yes.
And how long is normally the answer for the question? Because we have 3 hours, right?
Like it's up to you. You can answer one in 10 minutes and take the rest 50 minutes to answer.
But is it like a length of the text?
Like they have as much as they can write as much as they want, and 3 hours. Like you can always go forward and backward.
I think it makes sense to explain pretty much everything you know about the subject matter, but stay with the subject matter. Because sometimes there is a misthought from the students that you just explain about how was your summer vacation and recent trip to Lapland, and you think that because of amount of text we don't read it, but we just measuring. Oh, there's this much text. This is must be a full remarks.
And make sure to mention everything that is important. And
Yeah.
you don't need to describe everything in detail, but
No.
the most important thing.
It's
If
okay.
you answer
It's okay.
everything, yes, why not? It will make my life easier. So why
Yeah,
not?
but stay in a focus. Sometimes I made this advice that if you don't know exactly what we are asking, answer something that is related. Don't do that. Don't do that because it's going to make our life painful, really painful. So just focus on the subject matter.
And we answer the questions in a Word document on the PC there.
No, but it's like that. You open it in the browser, and basically there is a section that you can write your answer.
Okay.
You can either write in Word and then copy paste it, or directly write it down there.
Okay.
It doesn't make a difference. Pardon?
How is save? How you save your answer? How you upload your answer? You click like.
Like when you finish the exam, you just say it's it. Push the submit button. Yeah, and it will be submitted. It's like taking the exam in Moodle, but the difference is you have to be there. And like
But is it
have access
Modal?
to
Is it then in a Modal system?
No, like it's somewhere completely different. Then we have to
Ah.
export the result to Moodle. The
Okay.
platform is the exam.fee. It's completely different from Moodle.
Okay.
But it has access to Moodle. That platform. Yeah, it's you don't want to go there.
Okay.
It's not allowed to bring something to write.
You guys, I don't know. These are the. I think you cannot take a phone with you. Okay.
Not phone, not your watch, anything.
Because in the Modal announcement from you, it's like there's no eating and stuff and no drinking and stuff. So.
Because there are other people who are taking the exam for other courses. Drinking or eating, it might disturb them.
Okay.
But there are cameras.
Without drinking is quite hard. So.
But I believe that there is this possibility of going out, because what if you need to go to the restroom?
Okay.
But I think it's just so that there are cameras all over.
Yes.
Because some people are clever. They're writing the answers they hand, like this. The camera is looking you all the time. So then not a good idea. Okay, here's one more thing that is extremely important you to know, that the plagiarism is not taken easy here. Any kind of like wrongdoing in exam and plagiarism, it always goes to the director's office. And the director is not happy. He's a happy guy otherwise, but if he's gonna meet you because of any kind of like wrongdoing like that, he's a vicious guy.
So, but is it allowed to bring a bottle now or not?
I would say better
So why
not to
bring
take,
before
because it's 2 hours only. I would say play safe and don't take it with you.
Okay.
But then, for sure, you cannot take your computer with you. No notes.
No, like
Notes.
device.
Notes is not allowed.
Basically, only allowed to take your this electric key, and then you get you have the key for the lockers that are.
You leave your gears, you leave your audio stuff to the locker room.
Water or something is allowed?
No,
No, nothing.
except for the electric key and the.
Okay.
But one more question: is there somebody helping you? No. So it's like a place that you just go and do your exam and you go away.
But you have to find all the relevant information from A.
Yeah, there is some instructions like practicalities
Yeah.
what you can do.
And then
Okay.
You cannot have any. You have to leave your phone to the locker, and
Yeah.
if you have any kind of watch, you have to leave that also in the locker.
I like even watch.
Any kind of
Because
Any kind of watch.
because
We go in there, we take a PC, do we have a specific PC?
Yes.
Yeah.
Have you registered that, like your PC?
yes, you,
And some
When the exam automatically starts, or do you have to do
when you go there, first you book the time, and from the booking information, you can find that you have booked exam 009, for example.
Okay.
And this means for 012, this means you have computer 9 or computer 12. And the computers are numbered in the class of the table, and each table has a number.
Okay.
And you check the
Okay.
number you have booked, and on that computer, you start the computer, and then you log into the computer with the Modal credentials.
And I guess what not allowed is to communicate with others. You cannot discuss with others.
Not even a question. You can't talk at all. Or
Do we go in the room at the time we book the exam, or does it start at the exam?
Yeah, it starts at the start.
So I have to be a little bit earlier.
No,
There's like, in the instructions, it's recommended to be like 5 minutes earlier than
Ah, okay.
so you can log in and get ready, because the exam starts at the exact time you have booked
Okay.
the exam, and it closes at the exact time.
So what if you're late?
if you're late, you just have less time because
Okay, so not that big of a problem.
the exam is, you can, for example, if you book flight from 12 to 3, you can go there at 2, but then you just have the 1 hour left.
Yeah.
The time zone you have booked, it is
So-
time.
Okay, one more question. What if you're sick?
If you're sick, you can
Reschedule it.
reschedule the exam, and I think it is said that you should not reschedule it less than 2 hours before the exam. But of course, if you're sick, then
Okay, do you need to get the doctor's certificate some kind?
No.
Okay,
You can just maybe you can
all right.
reschedule it in any time, but I think there's a recommendation to do it like at least X amount of hours before the exam starts.